Good afternoon, everybody. Welcome to overcast, almost rainy Wednesday afternoon of Chem 170 with your host, me, Dr. White. Hi, everybody. All right, got a couple announcements to make. First of all, this morning I put in the system, I think you see it, I don't know really. ECC, all faculty have to enter what's called midterm grades, which is yeah, why? Well, I know why, because it deals with state aid, which is important. Now, the midterm grades I entered has nothing to do with what your final grade will be. It can still be a lot different, better, I hope, or worse. What I did was took your two tests, added them together, divided by two. It was 90 and above. I put down midterm grade A, 80 to 89, B. I don't think anybody was any lower. No. So again, midterm grades are just something we have to put in mainly for state aid that the school gets reimbursed for you being enrolled in my class and other classes too. So I wanted to let you know about that. All right. 2 weeks from today will be test number 3. I get that finger fixed. Test number 3. Ooh, that's broken too. Anyways, test 3, by the end of the week, I will put out an announcement and send an email of how many pages, I believe it's usually 9 historically, how many problems, no multiple choice. There'll be 3 areas like test 2, general knowledge, nomenclature, and reactions. There'll be about 3 to 5, I don't know how many, because I haven't written a test yet. That's this weekend's job for me, because every semester I rewrite a new test. And I'll put that information out. I can tell you now, test number 3 will cover carboxylic acids, carboxylate anions, esters, amines, my favorite, quaternary ammonium salts, and also amides, which we'll finish today, and we'll do most of heterocyclic compounds today, at least everything that will be on the test. So that will be test number 3 coming up. Now, speaking about coming up, if you look at the events calendar for Elgin Community College, oh, bright choice, bright future. I hope that's true for all of you. If you look at the academic calendar, it says March 27th through April 2nd, all facilities closed, spring recess, or really spring break, which means this week, next week, Monday through Sunday, the school's closed. And what that means is we will have no lectures. I'll post no videos. I will not have office hours, but I will promise this. Each day, I'll check my email at least once, possibly twice, but at least once. I don't have to, but each day I will. And that means next week, no class, no lab, no lectures, no videos. Now, if you have Dr. White withdrawal symptoms, you can always go back and look at my YouTube videos and watch me again. If you want, you can binge watch them. Nah, don't do that. It might be bad for your health. Then again, it might be good. But next week, no lectures, no labs on Monday and Wednesday. And what that means is the lab we're doing today is not due a week from today. It will be due 2 weeks from today, because next week is spring break. Any questions? Looking at the chat. All right, let's get to work. We got a lot to do today. We always got a lot to do, which is a good thing. All right, let's go through. Let me make it a little smaller. The carboxylic acid and ester problem set. And as always, you should do these to do well on the test. That's why I call them practice problems. You've learned that from test 1 and 2. All right, give the name, IUPAC name for the following molecules. Well, what do? You look for what's different. Let's look at C. Ooh, 2 oxygens, carbonyl, hydroxy group, R group, carboxylic acid. How do you name it? You find the longest chain with the carbonyl carbon double bond oxygen, name it as an alkane, 6 carbons, 2, 4, 6, hexane. For carboxylic acid, drop the E, add the letters OIC in the word acid. And that's hexanoic acid. The carbonyl carbon is number 1 always. Everybody knows that, so we don't have to put the number 1 there. Now, if we look at D, excuse me, we have 5 carbons, longest chain, pentane. Drop the E, add OIC, the word acid, pentanoic acid. Oh, look, it's your good friend, the methyl group. Remember, the carbonyl carbon is 1. It's on carbon 4, so it's 4-methyl pentanoic acid. And here I just have a little more interesting one. Now, let's look at F. This is a carboxylate anion. How do you know? The O minus, M plus. M can be sodium, potassium, or lithium. It can be other things too, but I'm limiting it that to this for this class. Now, there's 2 ways of doing it. Both involve in front the cation. You name that as the element it comes from, Na, sodium. Now, a very sharp student of mine, Chem 170 years ago, came up with a separate one from my UPAC that works perfectly, except when R is benzene. And that is, name the longest chain with the carbonyl carbon in it, 3. Propane. Drop the E and add OATE. Sodium propionate. Now, as my gift to you for this and esters, I will not put an alkyl group here. That's my gift to you. For carboxylic acids, yes. For carboxylate ions and esters, no. Now, when R is a benzene ring, you have to use the IUPAC method. That is, it's still named the cation as the element it is in front, potassium. If this were an H, that'd be benzoic acid. Drop the IC and the word acid and add OAT or ATE. So benzoic becomes benzo, and then add ATE, and that's benzoic acid. Now, H is an ester. Esters, carbonyl, oxygen with R prime, and the carbonyl has carbons R. Name the R prime as the alkyl group it is in front. And as I just mentioned for the carboxylate anion, if R here is not benzene, find the longest chain with the carbonyl carbon, name it as an alkane, drop the E and add OAT ending. And that's alkyl acetate. Now, just like we had with R being a benzene ring and carboxylate anions, that's the same way. Again, same thing. For an ester, you name the alkyl group R prime on oxygen as the alkyl group it is, methyl. Then pretend that's an H, benzoic acid. drop the IC and the word acid and add ATE, and you get methyl benzoate. All right, now, another nomenclature question is draw the condensed structures for the following organic molecule names. And here you have to know both common and IUPAC. And here, acetic acid, which nobody calls ethanoic acid, is that structure. Speaking of which, time out for a public service announcement from me, the management. Anybody happen to pick up a bottle of vinegar and think it contains acetic acid, which is a carboxylic acid? Do you happen to pick up a bottle of ketchup, mustard, or even relish, the green type we sell in Chicago that glows in the dark? No, it doesn't, but you know what I'm talking about, the good stuff. And if you look, it has vinegar in it, which has acetic acid in it, which is a carboxylic acid. Did you happen to look at a bottle of nail polish remover? Oh, see, I removed my nail polish. No, I don't polish my nails, but my grandfather had his done in the barber shop. They don't do that anymore. But anyways, did you look at that bottle and see it has ethyl acetate, which is an ester? While we're doing public service, when it gets nicer out, or if you happen to walk into a florist shop, did you smell the flowers and think, esters? You don't have to do the odd part, but esters. Or did you have a banana or other fruit or vegetable, or smell or taste it like a banana? I don't like bananas, but my mother and sisters, my mother did, my sisters do. And did you think, that's an ester? Or let's even go on. Did you look at your mouthwash and see it has quaternary ammonium salt or fabric softeners? Your sheet or the bottle, the sheet's better, is a fabric softener that makes your clothes nice and soft. All right, back to the problem set. Now here, if we look at C, how do you decode this to know what to draw? Start from the right, move left. OIC acid means carboxylic acid. That were E, 6 carbons, including the carbonyl carbon. On carbon 2 is an ethyl group. Now, this is a really nasty, dangerous, mean molecule. It was an impurity in an aldehyde I was using for research or reaction I had invented when I had to go back and do some more tweaking of that reaction. I opened up a new bottle of the aldehyde and the reaction stopped working. It was messed up. And it took me about 6 weeks of bad part of my life to finally figure out this is a new bottle. And I bought from that chemical company that sold the aldehyde. Was it pure? I had our analytical group. I was at EXO then. Who was the Dr. Chunan Wang was in charge of the analytical group. Gosh, was he a great analytical chemist? Oh, he helped me solve a number of problems. He came back and said that aldehyde has 35% of this acid, 2-ethylhexanoic. Boy, did that give me grief. And I realized I violated a key rule. And that's something that one of the best mentors of my life ever taught me, Sid Shapiro, who I met, he became my mentor when I was at Axo Nobel, and that was never assume or you become the first 3 letters, or as I like to say, you get burned. And I assumed, new bottle, open it up, it's good stuff. I bought from this company. After that, anytime I opened up a new bottle of a chemical, I had it analyzed. And also, so it wouldn't happen in our chemical plants, which I wrote procedures, I wrote in the procedure, analyze this aldehyde, and if it has more than 0.05 or 0.5% of this carboxylic acid, you can't use it. And that saved me more grief. It wasn't real, I hate that molecule. It hated me. All right, let's continue on. Let's look at F. How do you know what to draw? Start from the right, move left. OAT ending tells you it's either an ester or a carboxylate anion. How do you know which? You look in the front, you see a alkyl name, ethyl, it's an ester. If you see an element name, it's a carboxylate anion. So if this were an E, propane, the carbonyl carbon, the R prime and R in the ester, 3 carbons. The R prime on the oxygen, 2 carbons, ethyl. And cross off G, I shouldn't have put it down because I said I wouldn't put an alkyl group on the R of the ester. So cross that off. Now, common name, H, ethyl acetate. Nobody calls that except to say nobody calls it ethyl ethanoate. That's the structure you should know from the common name. Now, if we look at I, OATE ending, that can be an ester carboxylate anion. If that were IC acid, that would be from benzoic acid. With a sodium, that tells you this is sodium benzoate. Oh, cross off J. I stayed away this semester from magnesium. Just cross it off. Bad, Dr. White. I'm sorry. All right. Now, as I said, there are 3 parts to test number 3. One is general knowledge. Do you know ethyl acetate? This ester right up here is a nail polish remover. That's the general knowledge. All right. Now, the other thing is nomenclature, which we just did the 2 types. And the 3rd type of problem is reactions. And the reactions are draw the condensed structure for the following, for the organic product or products for following reaction. And here you look for what's different. As always, let's do B because it looks like fun. Now, you know, I'm an organic chemist. And what do we have that's different? Ooh, oxygen double bond to carbon with a hydrogen carbons. That's an aldehyde. Bracket O, close bracket, is shorthand for an oxidation reagent, such as potassium permanganate, sodium dichromate, and others, which I'm not going to even go down the list. There are a lot. And here's the general reaction. Aldehyde oxidized carboxylic acid. So the H here becomes a hydroxyl group OH, and you get this carboxylic acid. Now, let me remind you for test 3. Ooh, this is another public service announcement. Do you break carbon-carbon single bonds? No, never, except for 1 or 2 rare reactions. And we've already done that one, combustion, test number 1. So, do you break carbon-carbon single bonds? No. The other thing to remember is how many, oh, it's still broken. How many bonds to carbon? 4. 4 bonds to carbon. 4. That's my college ring. Should I? Oh, yeah. This is from IIT. Can you see the year? 1972. That's when I got my bachelor's degree. Ah, that was a long time ago. A long, nice time ago. All right. So remember, there's always 4 bonds to carbon, and you don't break carbon-carbon single bonds. Carbon-oxygen, carbon-nitrogen, yep, but not carbon-carbon. All right, let's get back to work. And here, if you look at D, it's an aldehyde oxidized. I've done the chemistry instructor's favorite trick on a test. I put a big, scary molecule. Ooh. But if you know the functional group and you know that R group just comes along for the ride, it's not big, it's not scary, and you can get the right answer. Now, when I look at this, I realize uh-oh, I forgot something. And that once in a while happens. And what's that something? This reaction. Under the right conditions, when you oxidize a primary alcohol, you'll get a carboxylic acid. So I better give you some practice problems. And here's one for you. Give the organic product or products for that reaction. Your turn. I forgot to mention, if you're going out of town somewhere nice for spring break, you can always email me a nice picture wherever you are. And in the email, you can write, having a good time, glad you're not here. And don't forget to vote yes when you're done. All right, I think everybody's done. So my turn. What's different? Ooh, oxygen with a hydrogen and a carbon. But we're oxidizing. Oh, in a brackets like that, oxidizing. This is a primary alcohol. And when you oxidize it, what do you get? A carboxylic acid. And I've actually done this reaction for my PhD thesis to make carboxylic acids. I need it. And what's our? This, because this carbon with the hydroxyl group is this one. So I have 1, 2, 3 methyl, then this carbon, which now is this carbon, and that's the carboxylic acid. I know there are 4 bonds to carbon, so I can put in my hydrogens. And this to be sure, 1, 2, 3, 4 across, plus 1 is 5. 1, 2, 3, 4, plus 1 there is 5. So I didn't break any carbon-carbon bonds. Now, I don't have it on the problem set, but you can take any problem that's fair game for synthesis, cover the starting material, look at the answer, and figure it out. But I'll give you one right here. What molecule do I oxidize to make that molecule? And this is synthesis is the fun part. At my level, when I worked in the chemical industry, and now even when I consult, the question is, what molecule will will have these properties for this type of product at this cost that can be made in existing plant equipment. And you don't even know what this is. You have an idea what functional group, but not the structure. And that makes it even more exciting, at least for me. All right, looks like everybody's just about done. I'll give you another couple of seconds. And now, how do you do this? Well, you look at the product and look for what's different. What's not carbon, what's not hydrogen, what's not a carbon single bond. Should get your attention like that. Ooh, oxygen, double bond to carbon, hydroxyl group, and carbons, a carboxylic acid. And this could have two answers, but you could use the aldehyde or the primary alcohol. But since we're practicing this, it's a primary alcohol. Well, this is a carboxylate anion. Carboxylic acid. What am I saying, anion? I got charges on the brain. All right. Oh, that was an awful joke. R is that. Therefore, I have my two carbons. This carbon, carbonyl, becomes this carbon of the alcohol. And a quick check. I ended up with 3 carbons. I better start with 3 carbons, and I do. And that's how you do this that I forgot to put in the problem set. All right, let's move on. Now, let's look at E. E, what's different? Carbon, ooh, magnesium bromide on carbons, Grignard. Now, I don't have here, but X can be chlorine, bromine, or iodine. And carbon dioxide, CO2, second step acid, and water. And here, you make a carboxylic acid that's 1 carbon longer than the R group you start with. Well, here R is ethyl, and this is 1 more carbon. Now, if we look at F, we have R is a cyclohexane ring, and we get this carboxylic acid. And A, I gave you a much more complex R group. Favorite trick on a chemistry organic test, put a big scary molecule. Woo. If you know what it's an R group, then it's not scary. If you don't know what you're doing, it's scary. All right, let's look at B. What do we have? Carboxylic acid. NaOH, that's a base, hydroxide base. I don't have here, but for this class, M can be Li, lithium, Na, sodium, or K, potassium. And this straight acid base, you pull off, excuse me, the acidic proton on the OH group, and you make a carboxylate anion. Here, M is sodium, you get this. Now, you don't have to show your charges. I do. I just think it looks cool. Did I tell you Dr. White's always trying to be a cool dude? Don't answer that. All right. And if you look here, I have R as a benzene ring, M is potassium, you got potassium benzoate. Uh-oh, D, don't look. That OH, should be ONA plus. The OH in D, I made a mistake. I guess I'm human. That's a good thing. All right, the OH here, that should be O minus Na plus. All right, now, on number 5, this is a very rare question I ask. Draw the condensed structures for all the products of this reaction. And if we look here, it's the first reaction I ever ran with my hands. Your body, when you were born, or I don't know, even before, is running reactions. But with my hands, my father taught me, remember the little rocket ship? You have a carboxylic acid, in this case acetic acid, which is in vinegar, NaHCO3 baking powder, and when you react it with a carboxylate anion or carboxylic acid, I got anion on the brain today, you get the carboxylate anion, carbon dioxide, and the arrow up tells you it's given off as a gas, plus water. And if you do it for R's methyl acetic acid, which is vinegar, if you mix vinegar and baking powder together, you'll get sodium acetate, water, and carbon dioxide. Remember the little rocket ship. And I have another R group. Now, remember, in tomato paste and tomato sauce, you have a carboxylic acid. And there, it's called citric acid. And my father's, I guess you'd call it invention, I never asked him if he came up with it himself or not. But when you're making a big pot of spaghetti sauce, near the end, first of all, when you make it, you cut back on the sodium chloride you put in there. Near the end, you put in a tablespoon if you have like a 3-gallon pot, a lot less if you have less, sodium bicarbonate, baking powder. You see it bubble up a little, and it increases the pH to make it taste milder, nicer. The other thing I don't know how he found out about was put a little pinch of cinnamon in there, but that won't be on the test. But remember, I told you the story. A friend of mine put like a 3-quart pot of spaghetti sauce, like a tablespoon. All you could taste was cinnamon. You couldn't even taste any tomatoes. All right, now 6A and 6B cross off. I didn't talk about calcium. It's correct, but just cross it off. 6A, 6B, cross it off. Now, let's look at E, or no, C. What do we have? Carboxylic acid. What are we reacting it with? An alcohol, ROH, R prime. H plus is acid catalyst, and this is Fischer esterification. The carbon with the hydroxyl group will be the carbon, the oxygen, the ester is bonded in R prime. The carbon with the hydroxyl group will be the carbon the oxygen is bonded to in R prime. So here R is 3 carbons, R prime 1, here's our ester. If we look at D, benzene ring is going to react with an alcohol and acid, but a carboxylic acid will. And notice the isopropyl alcohol, carbon is on, hydroxyl group is on carbon 2, the middle carbon. Therefore, this oxygen, the ester, is to the middle carbon. The benzene ring comes along for the ride. Now, reactions of esters. Here, I forgot to put the water down when I wrote the problem set. But take an ester, react with base and water. You'll get back not the carboxylic acid used to make the ester, but because you're in base, the carboxylic acid you get here immediately reacts to make the carboxylate anion, plus you get the alcohol you would have used to make that ester. Now, there can be other hydroxide bases, but for this class, I'll just stick to sodium hydroxide. So we look at H, ester. R is this benzene ring with a methyl group. R prime is ethyl. And you get this carboxylate anion, the carboxylic acid you would have used to make that ester, plus this alcohol. And I'll talk to you later about this or similar reactions I've used or we used when I worked for Unichem Chemical to make carboxylic acids and their derivatives. Now here, In 7A, what do we have that's different? Carbonyl, oxygen, R prime, R ester, H plus, acid and water. And by the way, where can you find acid right now where you're sitting in the room you're in? In your stomach. H plus can also be HCl for this reaction, which it is. We'll come back to this general reaction. It's called acid hydrolysis of an ester, because this is how your stomach breaks down fats and oils, which is a good thing to keep you healthy, unless you have too much. And ester, acid, and water, you get back to carboxylic acid plus the alcohol you would have used to make that ester. So if I have this ester, R is 3 carbons, I'll get this carboxylic acid, R prime, the carbon with the oxygen and the ester. The carbon with the oxygen and the ester will be the carbon that has the hydroxyl group in the alcohol, the center one, in this case, isopropyl. Just think about it. 6 months ago, would you know what I'm talking about if I said isopropyl? Maybe not. You do now. And if you notice B and C, all I've done is made different R groups. Now, finally, let's go to D, E, and F. And being an organic chemist, we usually don't balance it. So I didn't even notice. If I were talking to my colleagues, I would never put the 2 there because I know everybody knows that. I forgot to put the 2 there. On a test, I won't. So what do we have here? Ooh, a Grignard reagent with an ester. Grignard reagent. Second step, H plus and water, acid and water. And now you get to make not 1, but 2 carbon-carbon single bonds. And these attack the carbonyl carbon double bond oxygen of the ester. It kicks the OR prime out as a separate alcohol. And when I'm talking to colleagues, I say, and that gets kicked out. Organic chemists better watch out. We're violent. And you make your 2 carbon-carbon single bonds to what was the carbonyl carbon, and that becomes an alcohol. So in D, R is benzene ring, R triple prime methyl, you get this alcohol. R prime is methyl, you get this alcohol. On the problem set, I forgot to put the plus there, but on test I will. If you notice F, oh, did I have fun on that? And I hope you did too. R is an ester, 2 Grignards, acid catalyst. R is a CH2 cyclohexane ring. Attach that carbon. My R triple prime is an ethyl, so I get these 2 ethyl groups. That's the alcohol. My R prime is ethanol right here. And we're done with the problem set. We're done. Yay. Any questions? All right. Coming up soon, I'm going to have to talk about one of the dumbest things I've done in my life. Oh, is this dumb? Oi. Everybody know what oi means or oy vey? It's like, woe is me, oi. It's Yiddish. All right. On Monday, it seems like longer. On Monday, I started talking about amides. Amides are a derivative of a carboxylic acid. And they have this structure, which a better way of drawing it, my software likes drawing it that way. It doesn't matter which R is our prime and which is on the nitrogen, our double prime, it rotates around. Now, remember, for the amides, R prime and R double prime can, one, both, or none be a hydrogen atom. And that gives you different types of amides, primary, secondary, and tertiary, which you don't have to know. I mentioned it briefly, these types. All right, switches off. You can have a cyclic amide, and that's called a lactam. I'm not going to go into lactams in this class. Now, let's talk about a molecule at first glance. Remember, amide switches on now. And that's this molecule, which I'm going to write like this. And this is called urea. And it's a amide, even though this is our prime or R, which you normally think of carbons, urea undergoes most of the same reactions amides undergo. And it's the major ingredient in, when I say major, the major organic molecule or chemical in urine, both human and animal. It's a white solid in your urine. It's dissolved in water. In your urine, the major chemical is water. This is one of your body's ways. Now I'm going way beyond my knowledge of the human body. Did I tell you the last time I took biology was freshman year of high school? Wow, that was a long time ago. Not there's anything wrong with biology, but by then I already knew I wanted to be a chemist. Yep. But urea is a white solid at room temperature. And it can react with formaldehyde, and I'll teach you this later, to make very important urea formaldehyde polymers. And I worked for Borden Chemical, now called Exxon, and that was a major product. Quick Dr. White story. We're about to run a new reaction I came up with at the plant using urea. I don't know how many thousand pounds, about 2,000, 3,000. And urea comes in what's called super sacks. You know, these huge sacks, they have about 2,000 pounds. Let's see if I can find a picture of it. And there's one. Can everybody see that on your screen with the guys with the hard hats? Generally, in a chemical industry, it's sealed up like this, and you open it up and get the chemical out. Well, urea can cake, become a solid. And one of my less pleasant memories was we went to go use it and found it was all caked together and we needed it in pellets or small pieces to get it into the reactor. I and about 5 other workers spent the next hour with, I think they were 10 or 20 pound sledgehammers breaking it up. You do what you have to do to get things done in a chemical plant. It was a good workout. Wow, was that a good workout? So this is urea. All right, now, one of the nice things about my class is the question you should always ask is, why am I learning this stuff? Well, the obvious answer is someone told you have to take my class or 1 semester organic to get into a school or program. But why learn about this? Now, how many of you are familiar with peppers? You know, like red peppers, green peppers, habanero peppers, ghost peppers. They can be real mild or real hot. What makes them hot? Well, it turns out it's an amide. And the chemical that gives heat to peppers, and you don't have to write this down, click, switch in the off position, is this amide. Has the common name capsaicin. The more capsaicin, the hotter it is. Red peppers and green peppers, I think, have almost 0. You go to habanero, they've got some. And they measure that by what's called the Scoville unit measurement of heat. I don't know how they came up with that, but that's what they use. And the higher the Scoville number means the more capsaicin. Now it's time for me to talk about the dumbest thing I've done in a long, long time. Everybody's seeing I can bring my bottle up, but I won't. You see on your screen, the ground habanero chilies. This is from the Spice House. They have one in Evanston, one in Chicago, one in Milwaukee, but you can get it ordered. If your order is large enough, it's free shipping, which I do now. I don't drive to Evanston anymore. Why should I make a 45-minute trip each way when I can get free shipping? When it wasn't free, it was fun to go down there, but I haven't been there. They sell this. When they first started selling ground habanero, I bought a bottle and a jar, 2 ounces. And it's not cheap, but this is wicked. So what did Dr. White do? Well, I came home, this nice little shaker bottle of this brown powder. I wonder how hot it is. So here's the dumb thing I did. I opened the screw cap. There's a little powder on the top of the little cap with the holes in it. And I went like this. Mistake. Not only a mistake, I was in not hot. My lips, tongue, and everywhere in my mouth was instant pain. And I was thinking in about 3 seconds, do I have to go to the emergency room? It was that bad. Now, I'll teach you more in detail about this, but there's a rule of thumb, not really a law, but it's pretty almost true always, called like dissolves like. Things that are polar are soluble in polar things. I'll teach this in detail in about 2 chapters. And things that are nonpolar are soluble in nonpolar things. You try and mix the 2 together, they're not soluble. Well, capsaicin I knew was nonpolar. Water is polar. So I drink water, it's not going to get any of that off my lips, my tongue, which now it's really painful. I mean, painful, not just hot, pain. So luckily I can think very quickly in an emergency, and I've had to use that in a chemical plant, saved my life and others, but this was just for me personally. I said, I need something nonpolar. Now, what's nonpolar? Well, vegetable oil is nonpolar. Butter is mainly fat, nonpolar. And I was standing right next to my refrigerator, also by the drawer, which had my silverware. I opened it up, pulled out a tablespoon, and opened my refrigerator because I knew it was quickest to get, and pulled out a jar of mayonnaise. Mayonnaise, and I'll teach this later on the semester, is 50% water and 50% vegetable oil. And I'll teach you later on when I teach you like dissolves like. So I took 2 big tablespoons, put it in my mouth, swished it around like mouthwash, went over to my sink with the mayonnaise and tablespoon, spit it out in the sink, did it 3 more times, gone, stop. But capsaicin in habaneros, especially habanero powder, I think they have now ghost pepper powder, which is even hotter than habanero. When I make a big 3-gallon or 2-gallon pot of chili for friends and everybody coming over, I'll take that bottle and just go dink, dink. That's enough. And it gives it a nice kick. Won't blow your ears off, but it's got a good kick to it. Stuff's dangerous, but good. It gives it a nice floral taste that you can't get any other way. So think about how many of you have ever had the real hot buffalo wings? And what do they serve it with? some ranch dressing. Why? And because if you're, and also they usually have celery. Why? Because if your mouth starts burning, you can take some of the ranch dressing, which has a high level of non-polar stuff that helps it get it out of your mouth. Or if you've ever seen someone at a Chinese or Thai restaurant eat some of the red peppers that are blazing hot, what do they bring to help them out? A glass of milk. Now, the watered milk doesn't do anything. What does do it is the fat in the milk. And that's also where they tell you eat some bread with butter on it. It's not the bread, it's the fat and the butter. And now you know if your mouth is ever in pain, your tongue, from eating a hot pepper with capsaicin in it, you know how to get rid of it. I could have done shots of vegetable oil, but the mayonnaise was easier and closer to get in my house. Oh no, if I look at the time, it's time for a break. Let's take a 5-minute break. I'll be back in 5 minutes, about 1:58 by my clock, and I'll see you in 5. I'm back. Now, quick Dr. White show and tell. I don't know if you can see it. This is that dangerous stuff. I just got a new bottle in, but this is really good. But no, I'm not going to even open up the top. It's too dangerous. No. Now, normally when I buy from the spice house, I'll buy in bulk. And years ago, I bought a bottle. This is the only stuff I don't buy bulk to put in the bottle. I don't want those powder floating around and getting in my eyes, even if I had safety goggles on. Or the other thing, which I do repurpose, boy, this is old, is their chipotle chili powder, pepper powder. This is really good. It doesn't have a kind of kick the habanero. It's got a nice little heat to it, but the taste is phenomenal. And their cumin is the best you can buy anywhere. And their other stuff. I think I told you about their double strength vanilla. All right, let's get back to amides. Now, how do you make an amide? I have here ammonia. Let's skip this slide and you'll see why. Because you can take either ammonia or a primary or secondary amine to make an amide. And since I wrote these slides, I've come up with a better way of showing this. And what's that better way? Well, here it is. Carboxylic acid plus this. And the better way is take a carboxylic acid and if R prime and R double prime are hydrogen, that's ammonia, NH3. If R is carbons and both R prime and R double prime are hydrogens, that's a primary amine. If R prime and R are carbons, but R double prime is hydrogen, that's a tertiary amine. So what I mean is this can be ammonia. It can be a primary amine. I made a mistake. Hold on. It's wondering why it didn't look right. It's one of my rare mistakes. It's like this. R prime and R double prime. Now it's right. Sorry. So it can be ammonia, primary amine, secondary amine. And what's attached to the carbonyl carbon? And carbonyl is still there. And you replace the hydroxyl group with the nitrogen. And what's on the nitrogen? And remember here, R prime and R double prime can be hydrogen. And I worked for a company that made a lot of amides. And in an amide, this nitrogen has 3 bonds to nitrogen. And only a quaternary ammonium salt and a amine salt, you have 4 bonds to 4 bonds to nitrogen. All right, let's take a look at this. what do we have? A carboxylic acid. Here we have ammonia, and you can think of this like this, where R prime and our double prime are hydrogen. And what do you get? An amide. So what's our methyl? What's our prime and our double prime? Hydrogen. And you'll get this. Now you can have both hydrogens out, or you can just go like this, and you make that amide. Your turn. What would be the product or products for the following reaction? Organic product or products. You also get water, but you know how I feel about inorganic stuff, unless you got to worry about it. In a plant where you're making 5,000 pounds, then you're concerned about it. But here, and don't forget, if you need any help tonight from 6 to 7:15, I have my office hour. If you really need help and you can't make it to my office hour, let me know, and I'll see if I can arrange a Zoom meeting with you when we're both available. All right, let's do this. What's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Ooh, carbonyl, hydroxyl group. Carbons here, I'll call R a carboxylic acid. Then I have ammonia, which I could write like this, where R and R double prime can be, in our case, they are hydrogen. And now what do you get? You get an amide. What's R and R prime and R double prime? Hydrogens. So I have my R group, my carbonyl, then my nitrogen, R prime and R double prime are both hydrogen. I can write it that way. And you've just made that amide. Now let's look at this following reaction. And again, the question is, what's the organic product or products are the following? So let's look for what's different. I'll do this one. You know I'm going to share and I'll let you have some fun too. And what is the look for what's different? Oh, my brain got that. Must be near spring break. All right. What's different? What's not carbon? What's not hydrogen? Ooh, carbonyl, hydroxyl group. Carbons here, I'll call R. A carboxylic acid. Ooh, what's different here? Nitrogen with 2 methyl groups and a hydrogen. And I'll call these R prime and R double prime. And what do we get? An amide. So what's R? 2 carbons. This carbonyl is this carbonyl, becomes this carbonyl. Now I have a nitrogen, and I have 2 methyls. Now I could write it this way, which on a test I probably wouldn't if I were doing a synthesis. How would I write this? Notice on nitrogen, you have the same methyls, so you can also write it this way. On a test, you can write it either way. And that's how you make amides. So I better share one with you. Your turn. What would be the organic product or products of the following reaction? And remember, please be patient. I try and give everybody time to finish. And it's my turn. What's different here? What's not carbon? What's not hydro? Ooh, carbonyl hydroxy group R, a carboxylic acid. What do I have here? Carbons. Ooh, nitrogen. This is a primary amine, but I can write it this way. And remember, R prime and R double prime, one or both or none, can be hydrogen. And what do you get? An amide. What's R? This. One of these I can call this R prime or R double prime. And one of the hydrogens, if that's R prime, is R double prime. So the R group is attached to this carbonyl. And then I'll have this nitrogen. And one of the R groups, doesn't matter if it's going this way or that way, your choice. I'll go this way. I could have put it down here, is this N-propyl, the carbon attached to the nitrogen, R prime, is the carbon attached to the nitrogen in the amide. Oop, almost made a big mistake. And R double prime is a hydrogen. There are 4 bonds to carbon, and that's the amide you make. what two molecules, and by the way, let me make that a benzene ring. What two molecules would I react together to make that molecule? Remember, this is synthesis is the fun part of organic chemistry. All right, looks like you people had your fun already. My turn. I say fun enough, you might believe me, and it's true. All right, what's different in this molecule? Carbons are, carbonyl, nitrogen, and on the nitrogen, R prime and R double prime. Now, in our case, it's not, but R prime and R double prime, one or both or none, in our case, none, can be hydrogen. And this is an amide. And how do you make an amide? A carboxylic acid and this ammonia or a primary or secondary amine. This is R. One of these I'll call R prime, the other R double prime. If I look at this, R is methyl, so I get this carboxylic acid. And the secondary amine, it doesn't matter which side you put what. The nitrogen has a benzene ring, a methyl group, and a hydrogen. And these two will give that product. Oh, let's do one more, just one more. So I'm having fun. And here's one more for you to do. Have fun. I will tell you this. An amine will not, under these conditions, react with a benzene ring. Won't. All right, let's take a look at this. Well, I said this benzene ring will not react. So I'm going to call this whole thing with the methyl group R. What do I have? A carboxylic acid. What's different? Ooh, nitrogen with two R groups, which I'll call R prime and R double prime. Remember, bracket like this means two of these groups on that nitrogen. Our case is not, but just to remind you, R prime and R double prime can be hydrogen. It's not in our case here. So what do you get? An amide. So if I look at my carbonyl here, comes this carbonyl, this one right here. What's R? This benzene ring with a methyl group called the tool group. And then I have my nitrogen, and I could write two ethyls like this. Or I could have written it this way. Both are the same. On a test, both would be correct. Now, one of the things I've been doing more often, we'll even do it more often the rest of the semester, is the question, why am I learning this? And you should be asking that. And you already know the answer that I know. And that's because someone said you have to take this class to get in a program or a school. But why learn this? Well, why learn carboxylic acid, an amine, makes an amide? Well, let's find out. This amide you just made has an acronym. It's called DEET. DEET is short for N,N-dimethyl metaethylamide. And what is DEET? And here's the line method. It's the same molecule we just came. This is the active ingredient in mosquito repellent. They don't like the smell of it. Why? I have no idea. That's not an area of my expertise. But here's another way of the line method of writing two ethyls, the same benzene ring with a methyl. The carbonyl is meta 1,3 to the methyl group. This is D. Now, time for another Dr. White story, and this will help you out. One of the good things about my class is you're going to learn about things you use in your daily life. But before I say that, why learn these reactions? Because that's how we make things like insect repellent. Now, the active ingredient in insect repellent is the amide you just made, T. When I bought this house years and years ago, the first time after I just bought it, I've got to go mow my lawn. But I was younger then too. And oh, my own lawn, I'm a new house, I'm gonna mow it. So Saturday morning, about 8:39, I'm out, get my lawnmower, start mowing. All of a sudden, every mosquito in the neighborhood said, whoa, meal time. I just got attacked. I said, I had to stop, put my lawnmower away. I better get some insect repellent. So I don't go there that often, maybe 5 or 6 times a year. But I went to Walmart because it was closer than Target, that French store, Target. So I go in there, go by the place where they have the insect repellents, and they've got a name brand off. And then they have the Walmart brand. I pick them up. The Walmart is about 20% larger, same price. But then I look at the label. And let's see if I can find it. And you see they have their repel, and you can buy it off. And you can't see it, you can barely see it. Notice it's 25% more. This also had, are you ready for this? It had twice the amount of DEET in it per can. One was, I'm just guessing the numbers, 1%, the commercial stuff, the name brand, and the Walmart brand had 2%. So they give you more, they have twice as much chemical in what they give you of the active ingredient, DEET, and it's a little cheaper. Well, it's a no-brainer. I bought that. I've got not the spray can, I use the bottle, and I've been using it ever since. When I do my lawn or yard work in the summer, I put it on everywhere, in my head even, and it keeps the insects away. And that's why you're learning these general reactions, because they're used to make things you use in your daily life. All right, now that you have amides, what can you do with it? Well, you can react it with acid and water. And the acid I'm going to use is HCl. Why? It's in your stomach. And we're going to learn later in the semester, this is the reaction your stomach uses to break down protein. Protein, how many of you have heard the term peptide bond? Any of you? It's really an amide bond. I'm an organic chemist, not a protein chemist. And your body breaks it down. Let's look at this reaction. Wrong button. Right button. And sometimes I'll put this over the arrow. Now, an amide, remember R prime and R double prime, one, both, or none can be hydrogen. When you react it with acid and water, HCl is acid, you get back the carboxylic acid you would have used to make that. But the amine you get, since it's in the presence of acid, which is a base, amines are bases, you get the amine salt, not the amine. And I'll teach you later how Mother Nature uses this to help make amino acids soluble in your blood. So, amide, HCl, and water, acid hydrolysis of an amide, you get back the carboxylic acid you would have used to make that amide, plus the amine salt of the amine you would have used to make that amide. And like I said, I could also write it this way. And the question is, what are the two products you get when you react that molecule with hydrochloric acid and water? Acid and water. What's this? What's different? Ooh, carbonyl. Excuse me. Nitrogen. I'm getting all choked up over this good stuff. We're really getting into a lot of good stuff today. And this is an amide. Remember, our prime and our double prime can be hydrogen. In this case, one of them is. I can call this R prime or double prime. The other one, R prime or other, and this is R. And when you take an amide and react it with acid and water, you get back the carboxylic acid you would have used to make that amide, plus not the amine, because you're in base. The amine gets protonated, reacts with the acid to form this amine salt. And you need an anion. And therefore, what's our methyl? So this is a carboxylic acid. I would get what's our prime hydrogen, our double prime methyl, and I get two more hydrogens, Cl minus. Now, I could have also written it this way. Notice on this nitrogen, how many hydrogens are there? 1, 2, 3. Either way, on the test would be correct. And that's how you have acid hydrolysis of an amide. And here's one for you to try. And a test, I'd put a plus there to let you know there are two products. Now, if this were organic chemistry majors taking this 2-semester, I wouldn't put the plus there when I took it. My instructor didn't, but don't tell anybody I'm being nice. Shh, I'll do it for you. Let me help you out a little. There you go. All right, let's do this. What do we have that's different? Ooh, oxygen, nitrogen, carbonyl. Carbonyl has nitrogen. On the nitrogen, I have R prime, R double prime. On the carbonyl, I have R. It's an amide. And we are now reacting with acid, HCl, water. The reason why I don't use H plus is because you need a counter ion for the amine salt. And what do you get back? You get back the carboxylic acid you would have used to make that amide, plus the amine salt of the amine. And that's why I use HCl, not H plus, because you need an anion. So as all molecules in nature have a net zero charge. This is R. One of these I can call R prime, doesn't matter which. The other R double prime. And remember, not in this case, but R prime and R double prime can be one, both, or none hydrogen. In that case, I get this carboxylic acid plus, and it doesn't matter which side has the methyl, which side has the ethyl. I could have reversed it. And you get that amine salt. And that's how you do. Oh, let's do one more. Let's do a synthesis one. What molecule, when you react with HCl and water, gives those two products? Or give the starting material for the reaction that gives those two products? Boy, you people are really getting the hang of this. Thank you. See, I told you organic chemistry is fun. All right, what do we have that's different in these products? Carbonyl hydroxyl group on the carbons, carboxylic acid. Look for what's different, what's not carbon, what's not a nitrogen. And this is an amine salt. And remember, R prime and R double prime can be one, both, or none hydrogen. In this case, one of them is. I'll call that R double prime. I'll call this R prime. And I'll call this R. What do we start with? An amide. This thinking, today we won't have time, but the Monday when we come back after spring break, we'll get to play that fun game. Circle and name the functional group, 2 points each. For carboxylic acids, carboxylate anions, amines, quaternary ammonium salts, and amides. It's going to be fun. All right, so if we put it all together, what's our methyl group? I have my carbonyl, my nitrogen. One of these is an N-propyl. The carbon with the nitrogen here, it's a carbon bond to that nitrogen. And then our double prime was a hydrogen. And that amide reacting with HCl and water will give those two products. Now, if you can react an amide with acid, you can react it with base. And the base will use the sodium hydroxide. Now, let me rewrite this. Sodium hydroxide and water. I'll teach you when we get into fats and oils and also proteins, why this is a good thing to use for, I already talked about that product, cleaning out your drain, stop drain. Anyways, amide. Remember, R prime and R double prime can be one, both, or none hydrogen. Now, You don't get back the carboxylic acid you would have used to make this amide. Why? Because the carboxylic acid in the presence of base forms the carboxylate anion. But you do get the amine you would have used to make that, because amines don't react with base because they're a base too. And that's what you get. And if we look at this reaction, question is, what's the organic product or products are the following? We look what's different here. Ooh, carbonyl, nitrogen, R prime and R double prime. Anybody feel like deja vu when I write this over and over again? But it's important. R prime and R double prime both can be hydrogen or none or one. And I have R, amide. Base some water, and you get not the carboxylic acid you would have used to make that amide, but since you're in base, you get the carboxylate anion, but you do get the amine you would have used to make that. What's R? This. What's R prime and R double prime? Methyls. Therefore, this carbonyl becomes this carbonyl. What's attached to it, R, is still attached. Now, you don't get the carboxylic acid. You get the carboxylate anion. If you write a carboxylic acid, I'll mark it wrong because you're in the presence of base, an acid will immediately react. And then you'll get, and I can write it this way, this amine, or you can write it this way. These are the same. And that's how you have base hydrolysis of an amide. If I look at this time, it's time for a break. Let's take about a 5-minute break, give or take 30, 40, 50, 60 seconds. And when we come back, after we do one or more practice problems with the base hydrolysis of an amide, I have a very, very important announcement to make. Again, when we come back, I'll have a very, very important announcement to make. You'll just have to wait. See you in about 5. I'm back. Hopefully you are too. All right, let's do a couple practice problems with amides, and then I have that special and very important announcement. All right, we're talking about you take an amide based on water, you get not the carboxylic acid, but the carboxylate anion of the carboxylic acid you would have used to make that amide, plus the amine you would have used to make that amide. So here's one for you to try. And the question is, what two compounds you make when you react that molecule with sodium hydroxide and water? Your turn. And I'll wait until everybody's done. And everybody's done. So let's take a look at this molecule. What's different? What's not carbon? What's not hydrogen? Ooh, carbonyl. Nitrogen. On the nitrogen, I have a hydrogen and an isopropyl group, and I'll call that R prime and R double prime. I call this R prime, this R double prime. Ooh, and I've got carbons here. I have an amide. I can spell it. Must be getting near spring break because I can't spell near that. I can't spell most of the time. And we're reacting with sodium hydroxide, a base, plus water. Base hydrolysis of an amide. You get back not the carboxylic acid you would have used to make that amide. You get the carboxylate anion of the carboxylic acid because you're in the presence of base. But you do get the amine you would have used to make that amide. And remember, R prime and R double prime can be hydrogen. And if we look at this is R. So I'll have this carboxylate anion, carbonyl. As this is this, becomes this, O minus and A plus. Remember, there's 4 bonds to carbon. So I put in my hydrogens, my amine, R prime isopropyl. The carbon bonded to this nitrogen here. It's a carbon bonded there, and R prime. Oops, Forgot that. Then our double prime is a hydrogen. You add one more hydrogen. You could write it this way. I could also write it this way. Notice there's two hydrogens on that nitrogen. And that's how you do it. Now for a very important announcement. Everybody listening, as of this point, I will not be teaching you any new general reactions other than later in the semester, a slightly modification of one of them. We'll be doing no more general reactions, but we'll get to take the ones you've learned and go out into the real world and see where they play a role. We're going to have some fun, and we're going to do it in polymers, and then the good stuff. Carbohydrates, fats and oils, and proteins. All the good things, the main food groups in life. And that's my special announcement. So now, I never counted it, but a couple of years ago, one of the students did. I don't know how close they were. I've talked about this semester so far about 50 to 52 general reactions. I know about 450, 500. I don't have enough time to go over those. And some of them are very specialized that for this type, even a 2-semester organic, I wouldn't go over. But we're done with general reactions. Now, one thing I want to cover before we start our lab, come back to this stuff later on. We'll skip this and I'll come back. But I want to cover this. And that's heterocyclic compounds. Now, on this slide, the thing you should know, what is a heterocyclic compound? A heterocyclic compound, you should know, is a ring that contains carbon or contains carbon atoms and other atoms in a ring, different atoms. And those other atoms can be either oxygen or nitrogen. Now, I will tell you, now you don't have to know, it's the largest class of organic compounds in nature, and many are aromatic. 2n plus 2 pi electrons. That you don't have to know. But what is a heterocyclic compound? It's a ring with carbon and other atoms, and those other atoms are oxygen, nitrogen. Again, what is a heterocyclic compound? It's a ring with carbon atoms and other atoms, and those other atoms are oxygen and hydrogen. So if I ask you on a test, 3 points, what's a heterocyclic compound? Well, that's a ring with carbon atoms and other atoms. Those other atoms are either oxygen or nitrogen. I'm trying to think here. I don't think they're both. Now, I'm going to ask you to learn one heterocyclic compound, and that's pyridine. Pyridine, the common name, is the IUPAC name. And that's a benzene ring, or looks like one, where one of the carbons has been replaced by nitrogen. And this is pyridine. That's an important compound. My mouthwash, the quaternary ammonium salt, is made using pyridine. And another molecule making that into a quaternary ammonium salt, that nitrogen. Now, the bad thing about pyridine, it stinks. Not as bad as sulfur compounds, but pretty close. How bad is it? Think about taking a dead fish, putting it in a Ziploc gallon baggie in the middle of summer, putting it in your backyard, and coming back 3 days later, when the temperature's up near 90, and smelling it. Ugh. Well, that's how pyridine smells, like a dead fish that's been around for a while. but it's an important compound. And with that, I'll finish up. First of all, another important thing with what I've covered, I have covered everything that will be on test number 3. When we come back, the Monday when we come back, I will go through the amines, quaternary ammonium salt, amide problem set. Make sure you do it so you do well on test number 3, because you know why I call them problem sets by now, practice problem. All right, it's time for the lab. Today's lab is what? Well, let's find out. Today's lab is carboxylic acid. Excuse me, I hiccuped. And this is a carboxylic acid. Now here, the first thing we're going to do is find out the solubility of carboxylic acids in water. As we've done all semester, if we were face to face, you take a small test tube, put some deionized water in there, and put a small amount of the carboxylic acid, mix it like this, or use the vibro mixer, which are much more fun. Now, what I don't have here, what I'll ask you to do is draw the structures for each of these carboxylic acid. Acetic acid, propanoic acid, stearic acid, I'll teach you more about, but you'll have to look in on the internet. Go to your favorite search engine, put in stearic acid, and afterward chemical structure. Same thing with oleic acid. And if you were in the lab, you'd find out acetic and oleic acid are soluble in water, stearic and oleic are not. How can you tell? If it's homogeneous, the same throughout is soluble. If you see 2 layers like an oil vinaigrette dressing, it's insoluble. And that's part 1. Now, in part 2, this is fun. Oh, I'm sad. You get to use some really dangerous chemicals: lemon juice, tomato paste, acetic acid, which is really, we use vinegar, and stearic acid and oleic acid. And what you're doing is putting it in, reacting it with sodium bicarbonate. And as you learned in class, and we do it in water. No, we do it solid. I take it back. You get the carboxylate anion of this carboxylic acid, and the sodium bicarbonate makes carbonic acid, which immediately breaks down to CO2 plus water. And if it happens, this you'll see as bubbles. Now, when you add an acid with a base, what should happen is the pH increases. Remember, pH is a scale going from 0 to 14. Below 7, the solution is called acidic. At 7, it's called neutral solution. And above is basic solution. And we can measure this with pH paper. I think, how many of you have used pH paper? I think most of you have had general chemistry at ECC, you've used it, and that changes color. And if you look at the hydron ion, I always pronounce that wrong, you'll see on the side they have a little scale. The paper, this is what we use at ECC, everybody does. The more green or blue, the higher the pH, the more basic. In other words, 13 is very basic. Below 7, when it's yellow or red, that's acidic. And you can measure by a color change what's happening to the solution. And for this one, no, you don't have to draw the chemical structures of the carboxylic acid, even though you should know acetic acid for test 3. Lemon juice has citric acid, so does tomato paste, stearic and oleic use a carboxylic acid. And if you were in the lab, here's the initial pH, and after adding bicarbonate, sodium bicarbonate, that's the new pH. And with all those, you see bubbles. Now, I'd highly recommend to have some fun, look at these 2 YouTubes on your own time. And the second one started at 311. It's fun. Now, the last reaction is the reaction I have stearic oleic, and I took off the stearic. This should really just be this. But anyways, in this one, you'll be using a strong base. Now, here's what you're going to do. You're going to react in water some acetic acid with sodium hydroxide. You'll do the same with oleic acid. And what you get is a clear homogeneous solution. And what are you doing? This reaction. And you find out certain carboxylate anions are more soluble than the carboxylic acids. Now, the new thing you're going to do is the second reaction. This will be one. Then you take this product, and I'll write it again as a separate one because I'll balance it because students get upset when I don't. I don't need upset students, especially before spring break. If you take 2 of the carboxylate anions and react it with, and this we didn't talk about in class, magnesium sulfate, which is a magnesium +2, sulfate -2, right down there, MgSO4, you get an ion exchange. And what you get, the important thing, is this new carboxylate anion, a magnesium carboxylate anion. And notice you've doubled the weight from the original sodium carboxylate because you got 2 of the R groups in that molecule you just made. Now, does that make a difference in solubility? Well, that's what you're going to find out. And when you take the original solution, which is also called a soap solution, carboxylate anions, certain ones, I'll teach you more when we get into fats and oils, are called soaps, like you wash your hands with, certain ones. You'll notice the solution you started with where you made the sodium carboxylate soap, when you react it with the acetic acid carboxylate anion, you still have a homogeneous solution. When you have oleic acid, you see this gunky, I like that for scientific term, gunky white solid in the Erlenmeyer you're doing this in. Now, if we are face-to-face in a lab, when you're doing that, I come around and say, see that white stuff in there? Guess what you just made? Bathtub scum. And the magnesium or calcium ions, works better with magnesium in the lab, but in real life it's calcium, form this type of dicarboxylate salt, and that precipitates out and coats your bathtub and your bathtub walls or shower if you use a bar soap. I'll talk more about that when we get to fats and oils. Now, I'd highly recommend watch this video. And with that, the rest are the questions. Don't forget, the lab you did last week is due today or even tomorrow. Don't forget, I have my office hour tonight from 6 to 7:15 p.m. If you on Zoom, if you have any questions, stop by, say hello. Or if you just want to stop by and say hello. And next week, no lab. I like this, no lab, no lecture. Don't forget, practice. So I wouldn't say no organic chemistry, but practice, because 2 weeks from today, we'll have test number 3. By the end of the week, Friday sometime, I'll put out a announcement and send an email about the details about test number 3. With that, I'll say, have a great spring break. I'll see you a week from this Monday, because next week is spring break. I won't be here for office hours next week, but I will check my email at least once a week, once a day, not once a week. And with that, I'll say, gang gesund, goodbye. Stole that from Granny. Bye now.